All right, so we're officially recording. Um, we're in week 9, which is the end of unit 2. So 16, 17, and 18 sections today. And then we're going to talk a little bit about exam 2 since that's coming up then next week. So 3 web work sections. 16 and 17 are both probability related, and then section 18 is kind of its own beast, where it's totally, I shouldn't say totally different, but it's not anything like 16 and 17. We got a quiz, we got a discussion board, and I'm not really sure how it happened that discussion board 7 is due on the 27th. Um, I looked at that due date thinking, what the heck? So I must have had a typo, but it is what it is, so we'll just leave it. Um, I'm in the process of grading project 1s. I have one of my face-to-face classes completely done, another one halfway done, and then you guys are next. So depending on how my evening goes, I might be able to get through them all tonight. Otherwise, tomorrow is at the latest. So then next week is exam 2. Did you already schedule your exam?
Yes.
Excellent. Good work. So anybody else watching this, if you haven't, schedule your exam now. It's due Saturday at noon. But as we know from exam 1, not all testing centers are open on Saturdays. So get those taken care of. That means next week's session, which I will be here for on a normal Wednesday at 1 o'clock, it's going to be a question answer session. So if you have questions, I have answers. So we can do any problems over the practice test or topics in general, but I will not have anything prepared. It will simply be a question answer session. So that's next week. So this week we're getting through the 3 sections at the end of unit 2. So are you ready?
Yes.
Excellent. All right. Do you have any experience with probability in the past?
Didn't we do a little bit of it at the beginning of the semester?
I don't remember. I don't think so. I mean, I guess not in this way. If we did, we might have talked about it in a different format. Um, probability, it always starts as a fraction. You can talk about probability as a fraction, as a percent, or as a decimal. Oh, look, I even have that on here. Oh my gosh, high five to me. It can be written as a fraction, decimal, or a percent. So we might have talked about probability a little bit because we have dealt a lot with fractions, decimals, and percents. So by definition, a probability is just the chance that something's going to occur, right? So like weather, the weather every day is based off of probability. The 10% chance of rain, that kind of thing. So we have 3 rules of probability. You don't really have to have these memorized. You just have to be able to use them. So when we talk about probability, it must be between 0 and 1. If something has a probability of 0, that means it will never happen. So when we say there's a 0% chance of rain, that means there's no chance it's going to rain today. Cannot happen. On the other side, if you have a probability of 1, right, 1 is like 100%. This means it definitely will happen. So if we say there's a 100% chance of rain, that means it's probably raining right now. So generally, probability is somewhere between 0 and 1. But 0 is the lowest it can be, 1 is the highest it can be. If we have a bunch of probabilities together, like if we have Skittles, a bag of Skittles, and talk about probability of picking out colors, all of those probabilities from that Skittle bag, they have to add up to 1. And again, that's based off of the fact that 1 is 100%, and 100% means all. So if we're talking about all of our Skittles, well, there's their 100%. And how do we find probability? The number of ways it can occur over total possibilities, that's kind of the easiest way to put it. I always kind of think of it as what I want to happen over the total possibilities. Because generally when you're finding probability, the top is what you want. So that's kind of what we're going to think about. We're going to do a lot of different problems, looking at a lot of different wording, and really how to tell how that wording really leads you into the problems. So, okay, so there's the basic outline, blah, blah, blah. Now let's get into the actual mathematics behind it. So number 1, we're going to roll a 6-sided die. What is the probability of rolling a number greater than 1? Oops, wrong button. Okay, so a number greater than 1, that's what we want. So the top number we want greater than 1, and on the bottom we want the total possibilities. Well, if you think about a 6-sided die, how many numbers on that die are greater than 1?
5.
Exactly, right? 2, 3, 4, 5, and 6. So there are 5 numbers that are greater than 1. How many total sides are there?
6.
Boom. So your probability is 5/6. Now, if you keep it as a fraction, you have to make sure you reduce. Now, this fraction is already reduced, but we're going to get into some bigger numbers, potentially. And so sometimes it's easier to just change it to a decimal. So 0.833 would be our decimal approximation for this particular problem. Okay, so basically rolling a die. You go to Vegas and you're shooting craps, it's all probability. It's very, very entertaining. All right, now let's go to a probability table. The majority of this class deals with probability in terms of a probability table. So you can see we're talking about males and females, and then maybe their favorite colors, red, blue, or purple. Okay? So we're going to use the table below. What is probability someone likes red? You'll notice the way this is worded, probability someone likes red. We're not differentiating between males and females. We're just talking about people in general. And I often talk about if you can think through probability in words, the numbers are a whole lot easier to deal with. So what do we want? What are we looking for in this? What probability are we looking for?
The red total.
Red total, exactly. So what we want is red and out of everyone, right? So we're looking for the total. So how many reds do we have?
18.
How many total do we have?
80.
There you go. So that's that as a fraction. How do I change that to a decimal?
You would take 18 divided by 80.
Perfect. And that gives us
0.225.
perfect. So if you're out of this group, you would have a 22.5% chance of picking somebody who likes red. That's what that means. Right? We're thinking about part to whole. These are part to whole ratios, so we can talk about them as percents. When you're doing web work and you're reading the problems, you're going to see the word probability. You're also going to see the word proportion, and you may even see the word percent. These three P words are used interchangeably. Generally, probability and proportion, those two words, we will write our answers as decimals. And if they want percent, obviously you would write it as a percent. So that's kind of but I always call them the three Ps, probability, proportion, percent, always meaning the same thing. All right, so let's go to the next one. We're going to use the same table. So now go ahead, you do this one and just let me know when you're done. Probability somebody's a female.
0.5.
0.5, how'd you figure that out?
Because there's 40 females and 80 total people.
Exactly. So we're talking about females over the total, and we end up with 0.5. Very good. All right, so very straightforward so far. So now we're going to change the wording a little bit. Now we're going to choose, we want to pick out a male who likes purple. So in terms of words, now we want a male who likes purple out of the total. So how many males like purple?
10.
10. So we're looking for an overlap. So that now we have 10 over 80, which gives us 0.125. Sometimes we call these an and problem. You'll see, we want to choose a male and someone who likes purple. So that's the intersection of male and purple, which in this case is 10. So if you see the word and, that implies intersection, which is what we did right here. Okay. But again, the whole concept is exactly the same. What we want over the total. All right, now when we get to the word or, it changes slightly. Actually, I want a darker color. Okay, so this one we want a female or someone who likes red. When you're talking about and, both things have to happen, right? We wanted the male and the purple. Now we don't care. We want female or red. If we get female and red, okay, but we don't care. We want one or the other. So if you think about, here's female. So we want all the females and we want all the reds. The problem is this piece here is in there twice. And if you just add them up, right, you're going to have an overlap. Just because you're female and you like red, that doesn't mean you get counted twice. So the way I like to think of it in words, right, we want females or we want red, but we don't want to count the female reds twice. So we always say we subtract the overlap, which is the female red. So I always think, right, if you can think about it in words, the numbers will follow. So the word or implies adding, but you have to subtract the overlap. So female, how many total females do we have?
40.
So we have 40 out of 80 for females. How many reds do we have?
18.
Okay. But when we did that, we counted this twice. So if we subtract the female red, that's our overlap, we subtract 6 because we counted them twice. So remember, when you're adding and subtracting fractions, your denominator stays the same. So that's still 80. But now I take 40 plus 18 minus 6 is
52.
52. So our fraction is excuse me, 52 over 80, which comes out to be what? Kind of a decimal.
0.65.
0.65. So you got a 65% chance of picking somebody who's a female or somebody who likes red. And that's what we're doing. All right. Does that make sense? How that
Yes.
one's a little bit different?
Yeah.
All right. Then. All right. Now we get to what we call conditional probabilities. So what is the probability of choosing someone who likes blue, given it is a female? The word given, also the word if. These are kind of the two key words. So now they're telling you, given it's a female, you know it's a female. So you're only dealing with the female line. You don't care about the males at all. So given that it's a female, well, now my denominator is going to be 40 because my total is just total females. Because that's all I care about, right? Given, female. Whatever follows given, or if, whichever word they use, whatever follows that, that's your denominator. So female's my denominator, and I want blue. Oops, the words are over here. So when I'm looking at my female row here, I know that the total is 40. How many of those like blue?
26.
Exactly. So my fraction is 26 over 40 because I'm only dealing with that female row, leaving me with, again, a decimal of 0.65. So 65% of females like blue because females there, it's still part to whole, but the whole, instead of being everybody, the whole is just all the females. Still all, it's just now a specific group. Does that make sense?
Yeah.
All right. So that's conditional probability. And that's section 16 in a nutshell. Talking about probability, the and, or, in conditionals. So really, it's as long as you really pay attention to the wording, probability, not too bad, right? Writing a fraction, changing it to a decimal. You just have to make sure you're paying attention to your wording. Any other questions on probability?
Nope.
Okay, so section 17, we're going to build on that probability. And this section, I think it's very interesting, but it can be a little bit difficult. So sometimes it takes people more practice to get it. Once you get it, you're good. But I don't know if you normally watch the videos that go with the packet as well as attending class, but for section 17, it might be worth it to watch a few. And if you just want more, you don't want necessarily the work in the packet. In the back, like page 348, 349, those are more just practice problems with less wordiness. And there are videos that go with all of those as well. And just the more practice you do with these, the easier they get. Okay, anyway. So false positive, false negatives. Do you have any experience with false positive, false negatives?
I don't think so.
Okay. I would say they're most common in terms of medicalness. So a false positive means, well, first of all, just kind of in general, false positive, false negative. The word tells you, positive or negative, tells you how you tested. False means it's wrong. So if you think about a false positive, it means that you tested positive for something, but you don't really have it. So you might have taken a pregnancy test and the blue lines show up or whatever happens, I don't know. And it's, oh my God, I'm pregnant, right? And then you freak out, but it's wrong. So we call that a false positive. You tested positive for pregnancy, but it's not true. Does that make sense?
Yeah.
Okay, so false negative, same concept. I have strep throat on here, but false negative in terms of pregnancy, right? You pee on the stick, nothing happens. You think, okay, I'm not pregnant. And then 3 weeks later, you find out, oh no, you really are. So false negative means you test negative, but it's wrong. And you really are pregnant or sick or whatever it is you were tested for. So you have to just remember whatever the word is, positive or negative, that tells you how you tested. The false part just tells you that the test was wrong. So this could be drug tests, medical tests, any kind of test really. So, okay, so with this, what we're going to do is we're going to create the probability tables. So in these previous problems, why can I not go backwards? Right, in these problems, we were given the probability table and we found them from there. Well, now we are going to create our own probability table. We are going to have to fill in the numbers. Then you can answer questions about it. So that makes these just a little bit more difficult because you have to create the probability table. So here's one example, and that's why I say the more you do, the easier it gets, because you start to see how they're all very similar. Just a few numbers change, but the process is the same. So here in number 7, 3% of people are allergic to snakes. This is completely made up data. A test with 92% accuracy can be used to test for this allergy. Use a sample of 50,000 to create a table, and then we'll answer 4 questions about this. So first things first, when you are creating these probability tables, you always, always, always need to start in the total column. If you don't have that column figured out first, you're toast. There's nowhere for you to go. So in this case, they tell us to use 50,000, and that's a total, right? So our total is 50,000. So that's a good start. Now, do you have any idea where to go from here? Or you want to guess where to go from here?
Probably the 3%.
Okay, excellent. What are we going to do with that 3%?
Take 3% of 50,000 to put them in the has allergy.
Perfect. So of means to multiply, and we have 50,000 people, right? So in our has allergy, we will take 3%, 0.03 times 50,000 people. Exactly. $1,500. Okay. Now, using your super skills, if you have 50,000 people total and 1,500 of them have an allergy, what do you know?
48,500 don't.
Exactly. So for all of our friends who are going to watch this later, right, we take that 50,000 total and we subtracted the 1,500 we had, and that gave us our 48,500 that don't have an allergy. So you've got to start with your numbers. How many have it? How many don't have it? Then we play what I call the inside 4. The inside 4 is where the accuracy rate comes in. Okay, and part of this is thinking through logically. If you are allergic to snakes, let's pretend you are actually allergic to snakes. If you go into the doctor to be tested, how would you expect to test? If you are allergic, what's that?
Positively?
Exactly. I mean, this works for strep throat, pregnancy, anything. If you're shooting up heroin and you take a drug test, if you have the issue, you would expect to test positive. So this is the accuracy rate would go, if you have the allergy, you expect to test positive. So 92% of people that have the allergy will test positive. So how do you think mathematically we're going to find that number?
Take 92% of 1,500.
Exactly. Accuracy rate, 92%. 92% of those that have it will test positive. That gives me 1,380. Okay, again, I'm going to call it maybe even just common sense. How do we find out how many of them will test negative?
Take the total minus the positive test.
Exactly. If you have 1,500 people and 1,380 of them test positive, well, then 120 are going to test negative. Because those two numbers together have to equal 1,500. Then when you go down to our poor people who do not have, well, I guess they're lucky, the lucky people who do not have the allergy. So if you're good, you're clean, you're not sick, if you go in and get a test, you would expect to test negative. So not having the allergy, expect to test negative. So that's where the accuracy comes in. So 92% of my 48,500 non-allergic people will test negative, which should come out to be 44,620. And then the same process, if I have 48,500 people total who do not have the allergy and 44,620 of them test negative, well, then 3,880 of them are going to test positive. What's our last step for this table?
Fill in the totals.
Exactly. So I end up with 5,260 positive tests and 44,740 negative tests. You might want to do a quick add of those two totals. Make sure that your positives plus your negatives equal your overall total. If they don't, you got an issue. But ours do, so we're good to go. All right, questions on how we made that table?
Nope.
All right, you seem to get it pretty good. Do you have that written down?
Yes.
Excellent, because I don't have it on the next couple slides, so you can reference your paper, I'll reference my paper, and we'll have a charming conversation about this. Okay, so using that information, 7A, how many false positives are there? So remember, false positives test positive, so you're only looking at the positive column, but it's wrong. So what number would that represent?
3880.
3880. Because if you test positive, you should have the disease. And if you don't, it's false. Well, that means you don't have it, but you tested positive, so 3880. Good. Okay, 7B, how many false negatives are there? So now you're testing negative, but it's wrong.
120.
There's 120. Yep. Okay, so far so good. Now we get into some probability. Given a positive test result, what is the probability someone does not have the allergy? The key word here is given. And again, sometimes it's going to be the word if. Whatever follows that, positive test. So I know my denominator is going to be positive test. The numerator is whatever the probability is going to be. What is the probability someone does not have the allergy? So the top is does not have. So now we are isolated in just the positive test line. How many positive testers do we have?
3880.
Well, those are the ones that do not have the allergy. And then what goes on the denominator?
The total, so 5260.
Exactly. So the total number of positive testers is 5260. Out of those, 3880 do not have the disease, and this would be your fraction. And this is a good example of a fraction that you don't really want to spend time reducing. That takes a lot of time. You don't need to do that. you can simply change it to a decimal. And we can say 0.738. Now, as a percent, that's 73.8%. It's almost 74% of positive testers that don't actually have the allergy. That might make you question, well, what's the purpose of this? If 74% of them are false positives, is this really a good test? Do you see what I'm saying?
Right.
So that is something that comes up with different tests. That's why we do this. That's why we talk about it. All right, let's try one more. I'll have you try this one. Given a negative test result, what is the probability someone does have the allergy?
.27%.
Oh, I hit a button. 0.27%. Yeah, you took it out farther than I did. Yeah, what was your fraction, just for fun?
120 over 44,740.
Perfect. So you get your total of the negative tests on the bottom and the ones that do have the disease on top. Comes out to be 0.0027. Change it to a percent, 0.27%. Very good. So the hard part about section 17 is creating that table. As long as you get the table down, then it's just a matter of answering probability questions, which is what you practice in 16. Or you will practice in 16, I suppose. All right, any questions on false positive, false negatives?
Nope.
All right, you seem to go through that pretty well. So that's good. Oops. All right, the last section of the day is margin of error. This one is pretty straightforward. I always think it's one of the easier sections, but we get into 95% confidence intervals, which sometimes confuses some people. So hopefully I can explain it today without too much confusion. This is, again, part of our statistical portion of this course. If you take a pure stats class, you're going to do confidence intervals of all sizes, and we do so with a big formula. In this class, we kind of just briefly touch on this, and we only estimate 95% confidence intervals. So it's hard to, I teach statistics also, so it's hard for me to kind of think through how we gloss over this. I don't know, I struggle with this. But anyway, it is what it is, so here we go. So the population, do you know the difference between a population and a sample? And it's okay if you say no.
Not really.
Okay.
No, I guess.
So the big key is that the population is all. And it doesn't have to be all people everywhere. It's just all of whoever you want to talk to. So if you want to do a survey of, college students, the population would be all college students. Well, is it very likely that you're going to be able to talk to all college students?
No.
No, that's crazy. Like, the population is huge generally. So the sample is a number. It's basically a subset of a population. So the population is all the people, and the sample is the actual number that you did. So in the example that I just threw out, the population might be all college students, and the sample might be 300 college students, because it's the actual number you talk to. Right? Makes sense. If you want to survey all adults, you're doing a political survey. So all adults, because everybody 18 and older can vote. Well, so the population is all adults 18 and over. You can't talk to all of them. So the sample might be 2,500 adults 18 and over. So the big key, that's the difference. Your population should, I just didn't mean to erase. Can I undo that? No, I can't. Okay, so population is all, the sample is the number. That's what you need to keep in mind when you're writing these. So, okay. So a margin of error. You are never going to be exactly right. You know, when you're using a sample, that sample is used as a predictor for the entire population, but it's never going to be perfect. So we talk about this margin of error as, you know, giving yourself a little leeway. You might see this if you've looked at surveys or tables where they've shown data that they've collected. Somewhere in a corner, it might say like plus or minus 3%. This is very good when we're during an election time because they use populations and samples and margin of error and confidence intervals all the time. But unfortunately, we are not at that. Well, I shouldn't say unfortunately. I'm thankful we are not in an election time. Okay. So margin of error is found by taking 1 over the square root of n. This is kind of our formula. And this is on your formula sheet, 1 over the square root of n. And it's only good if you know what n is. Do you know what n is?
The mean? No?
Nope, that's mu. I appreciate the effort, though. N is your sample size. Because the larger your sample, the smaller your error. And think about it. If you want to talk to adults that are going to vote, and you talk to 10,000 adults, that's a big sample. You're going to get a lot of different opinions. You're going to have some pretty accurate data. So you're going to have a small error. If you're doing this survey and you talk to 20 adults, that is not a very big sample. You're going to have very small survey of opinions. You're going to have a very large error. So your sample size will determine how large your error is. So the number from this part here will determine that. So 1 divided by the square root of n. We're going to want to make sure that you know how to use your calculator with that because that is crucial. Okay, so these actually go together because this 1 over the square root of n is an estimation for 95% confidence. So when they talk about finding your 95% confidence margin of error, this is the 1 over square root of n formula that we're dealing with. The confidence interval is a 95% confidence interval because that's the only one we're dealing with. And to find the confidence interval, we are going to take, in stats, we call it a point estimate. And this will make a whole lot more sense when we do an actual problem. The point estimate plus or minus your margin of error. So if I'm running for Congress, and maybe the point estimate, we estimate that 30% of people in Indiana would vote for me. That would be our point estimate. And our margin of error is 4%. Right? So just let me change colors real quick here. So if we say our point estimate is 30% and our margin of error is 4%, well, then our confidence interval, 30 minus 4 is 26. 30 plus 4 is 34%. So we would say we can be 95% confident that on election day, between 26 and 34% of Indiana people would vote for me. That is the purpose of this, to kind of get an idea of what's going to happen in the future. So we use that 1 over the square root of n to get the margin of error, which leads to this interval. And we are always 95% confident. It leaves a little bit of room for error, right? I'm allowed to be wrong. I'm only 95% confident. I'm not 100% confident. Okay, are you ready to jump in and do a problem?
Yes.
Okay, so basically these are kind of the questions that we're going to answer as we work through one of these. Okay. A recent survey of 2,400 U.S. adults found that 36% of adults think the Cubs are overrated. I forgot I used this example. This is made up data as well. I just don't like the Cubs. So when we're looking at this example, questions A and B kind of go together, the population and the sample. So who did we talk to in this problem?
2,400 adults.
Okay, so when you have the actual number, 2,400 U.S. adults, is that going to be the population or the sample?
The population.
If you're using the number, that's the sample. The sample is actually how many you used, right? So 2,400 U.S. adults is the sample. That's the actual number you talked to. The population is all people you could have talked to. So you would just say all U.S. adults. because you could have talked to, all 300 million adults. I don't know how many there are. But you didn't. You only talked to 2,400. So the actual number is the sample. The population is all possibilities. Every person I could have talked to. See the difference? Okay. So now we go into the margin of error. So our formula is 1 over the square root of n. What is n?
2,400.
There you go. So 1 divided by the square root of 2,400. Now, depending on your calculator, you might be able to do this all at one time. So you can try that. If you can't do it all at one time, the square root of 2,400 is approximately 48.99. So you'd find the square root first and then divide. You've got to kind of just figure out what works for your calculator. Just don't forget to take 1 divided by your answer. That's huge. What'd you get?
0.0204.
Perfect. We'll just stop at 2. 0.02. Change that to a percent.
2%.
2%. So our margin of error is 2%, meaning we can expect to be wrong one way or the other by 2%. So that leads us to our 95% confidence interval. What is our point estimate? What did we estimate people? What percentage?
36.
36. So we take our point estimate of 36%, and we would say that's plus or minus our margin of error, which is 2%. So the low end of my confidence interval, what's 36 minus 2?
34.
34%. And if we take 36 and we add 2?
38.
38. So our confidence interval is between 34% and 38%. So when you get to the part E, writing a sentence to interpret your answer, your confidence interval, and use your confidence interval in a sentence, I almost think of them as Mad Libs. Do you remember Mad Libs?
Yes.
Okay, where you kind of have things and you just fill in the pieces. So you always start with, I'm going to change colors for the different pieces. You always talk about how confident you are. We are 95% confident. Always. You always talk about your confidence. So we're 95% confident that between 34% and 38%, so now we got our confidence interval. Then we talk about who did we talk to? Well, we talked about of U.S. adults, and we use this to make an inference about the entire population. So we're 95% confident that between 34% and 38% of U.S. adults, and then it's, well, what are they doing? Well, think the Cubs are overrated. Boom. So you've got these 4 pieces. First piece is always the same no matter what your problem is. We're 95% confident. Then you go to your confidence interval, followed by your population, followed by whatever these people are doing. You get that from your main problem. So you've got four pieces. So the math behind this section is not difficult once you understand how the terminology kind of fits together. Questions?
Nope.
It's a little bit of practice, not bad at all. All right. Have you started project 2?
I just finished it today.
Oh, very good. All right. Did you already turn it in?
Getting ready to, yeah.
All right. Well, you're way ahead of pace, and that's great. That's great. So just to go back to the beginning there on what's due. I hate this stupid computer. 3 sections. We got a quiz, a discussion board, and project 2. If you want, I mean, project 2 is not due until, when is project 2 due?
The 27th.
27th. Thank you. I don't know why I didn't put that on here. If you want to like maybe hold on to your project until I give you feedback on your first one, I try to get the feedback out before the next project is due. That way, if you make one mistake on project 1 and I don't tell you about it before you turn in the next one, you're likely to make the same mistake. Does that make sense?
Yeah.
But I should have the project turned around between today and tomorrow, just in case you want to check that out before you turn it in. That's up to you entirely. It doesn't matter to me. But I'll shoot to try to get those done here shortly. So, any other questions for me, or we can be done for the day?
I think I'm good.
All right. So you already have your exam scheduled, which is fabulous. So as you're kind of working through things, if you have any questions that come up, you can jot them down, and we can talk about them next week. If you don't have any questions, you kind of have next week off in terms of the class. But yeah, awesome.
All right. Thank you.
Yep. Have a great day. Let me know if I can do anything for you.
You too. All right. Bye.
Bye.